So it's Frank Ball from Nottingham, the first of two speakers with exactly the same title.
Okay, thanks very much, Dennis. First of all, I'd like to thank the organisers for inviting me here. It's really a great pleasure to be back at the Newton Institute. I have very fond memories of the programme 20 years ago, and it's also had a big influence on my own career. And Dennis has asked me to talk a bit about the future. I find that rather difficult, but if I think back before, the one thing that perhaps I did with Dennis and Giancarlo whilst I was here before was to work on the households model. But before that meeting, I had no idea at all that I'd be working on households models. So I think it is quite difficult to try and think, well, what's going to happen in the future. Okay, so this presentation is joint with Tom Britton. I'll say a few words of orientation at the beginning, and we split this topic up of stochastic models into two bits. I'll be talking about emerging epidemics and the early stages of an outbreak, and Tom will focus on what happens beyond the initial phase of an outbreak. So given an outbreak takes off, what happens next. There'll be a number of sort of problems mentioned certainly in both parts of the talk, but I think Tom is going to collect these together at the end of a couple of slides. Okay, so first of all, perhaps we should ask the question, when are stochastic models needed? Well, I guess the answer, everybody knows the answer when numbers concerned are small, like at the start of an outbreak, or at the end of an outbreak when there's few infected left, so if interested to the time to extinction or fade out. When there's small populations of subgroups, like the experiments that Mark de Jong was describing yesterday, and I won't be addressing that in this talk. Or when you've got smaller units within populations, such as households or workplaces. And also, if you want to do any sort of inference or estimation, you really do need a stochastic model underlying your data. Well, the focus is going to be on what one might call simple stochastic models, for which some analytic normally fully... Sorry?
Can you turn the microphone on? There's a button on the top of it.
Is it not turned on? Okay.
Hold it down.
Hold it down for a while.
Okay.
Good.
Okay, is that...
Thank you.
There you are. Okay, so the focus is going to be on simple stochastic models, which some analytical progress is possible. So I won't be talking about complex agent-based simulation models. They, of course, are an invaluable tool for informing public health policy owing to their far greater realism, but they probably also miss some features. Typically, they require numerous parameters to be estimated, and they can be more difficult to interpret and perform sensitivity analysis on. And I won't be talking at all about deterministic models. They're appropriate when all numbers concerned are large, and of course they're usually easier to analyse than stochastic models. But these different modelling approaches all complement each other. For example, complex agent-based models may suggest features which you may want to analyse in more detail with simpler models just concentrate on those features. And simple models might actually suggest important things that must be kept in more complex agent-based models. Okay, so what about the early stages of an outbreak? What might be the key questions? Is a major outbreak possible, which of course related to R0? If so, what is the probability of a major outbreak? How fast will it spread? What will be the exponential growth rate? What about estimation in the event of an emergent outbreak? And also, of course, control measures such as vaccination strategies. And I think all of these questions and issues can be addressed to some extent using branching processes. So let me just give you a brief reminder about general pump mode Jaeger's branching process. So individuals have independent and identity distributed life histories, which consist of R, which is a typical individual's age at death, and a point press psi of ages at which that individual reproduces. So if this life history is is here, so if this individual is born at time b and TOR1, TOR2, etc. are the points of this point post-stress psi, then that individual has one child at each of times b plus TOR1, b plus TOR2, etc. These all are independent identity distributed. and then you can just piece them together to give, in an obvious fashion, to give you a population process. And such a process will approximate the process of infectives in the early stages of an epidemic in a large, closed, homogeneously mixing population, where now I is just the sum of the infectives later in the infectious period, and psi gives the infectious ages at which an individual creates new infections. So the approximation works because of the homogeneously mixing assumptions. Another way of thinking about that is each time a contact is made is with somebody chosen uniformly from the whole, at random from the whole population. So early on, you're unlikely to contact the same person twice, and therefore all infectious contacts result in new infections, and you get a branching process. Okay, was two or three main results which we'll be using. So we equate extinction or survival of the branching process with a minor or major outbreak. So if capital R is the number of offspring of a typical individual, and R0 is the expectation of this random variable R, then extinction occurs with non-zero probability, probability less than 1, if and only if R0 is larger than 1, and you can work out the extinction probability from the PGF of the offspring distribution. And of course, this extends to multi-type processes. So if you've got J types of individuals, then R0 is the maximum eigenvalue of a mean offspring matrix. But in the epidemic context, you're going to need all the numbers of all these types to be large to apply this theory in its sort of standard form. And the other result we mentioned, we'll be using briefly. So if Z of t is the number of individuals alive at time t, and in the case where R0 is larger than 1, and if there exists a Malthusian parameter R, which solves this equation here, where this is the mean measure of the offspring distribution, of the offspring random variable, offspring point process of the individual, that's given by this expression here, then e to the minus rt times Z of t tends to some random variable w, which is non-negative, of course, and it equals 0 if and only if the process goes extinct. And so this equation here gives you the real-time growth rate corresponding for an epidemic, given it takes off. Okay, so that all works as sort of homogeneously mixing models work, or locally large models. We can now come on to sort of households models. So here you have a population of a large number of small households. I'm not going to go into any detail about this, but essentially you have two main sort of parameters involved. Mu g is the expected number of global contacts made by a typical individual. So in this model, global contacts are with an individual chosen uniformly at random from the whole population. And then you have a sort of enhanced spread within the households, and mu h here is going to be the household size bias, mean final size of a typical single household epidemic. So early on in this model, what happens is you look at it at the process of a level of households. So you have spread within a household. When you get these global contacts, and these are going to be typically within households that haven't been contacted. And so at the households level, you can approximate what happens early by a branching process, and the threshold parameter, or one of several threshold parameters, is what's known as R star, which is just the product of the mean number of global contacts made by an individual by this size biased mean house size of a single household epidemic. And this slide was actually for another talk, but given what Peter said yesterday, these numbers here give the generations of infection. So you've got to start off with generation 0. These individuals are one away from that guy, so generation 1, and so on. And if you look at the limit as n goes to infinity of the mean number of individuals in generation n to the power of 1 upon n, that corresponds with Peter Trapman's definition of R0, and it also delivers the R0 which Lorenzo told us about yesterday. Obviously got to speed up. Okay, so I'll skip this and just go on to the next model, which is the households workplace model. So now you've got 3 types of contacts: global, within household, and within workplace. So we have the same sort of parameters as before, and you can now approximate this by a 3-type branching process. So you've got individuals which are called double primary. They're infected by a global contact. You've got individuals which are called household primary. They're infected through a workplace, so they're the first case in their household. And you've got individuals which are workplace primary. They're infected through a household, so they're the first case in their workplace. and you can write down this sort of 3 by 3 mean offspring matrix, and the maximum eigenvalue of that gives you a sort of Ri, which is a threshold parameter. Okay, that's all very well, but when you think back to what assumptions this actually makes about how these households and workplaces are configured. So what essentially you're doing, if you start off with one individual here, say, you have a spread within its, well, I haven't shown the spread within its household, then they go into workplaces, then to households, then to workplaces. And what this is implicitly assuming when you make that branching process approximation, that this sort of set of households and workplaces you get, they form locally a tree, and then it's not going to come back on itself. And that's rather unrealistic. And so although this model, I mean, you put the second level of mixing in, it has a significant effect, this is rather magnified and not realistic, because there's no sort of, essentially you just get this locally tree-like structure, and I don't think in real life that's what's happening. So, and a similar sort of assumptions are made, I think, in perhaps all mathematically tractable models of random networks which have a clustering in them. And I think one of the challenges is to develop more realistic models that are susceptible to analysis. I'll come back to that briefly. So now on to network models. So we've already heard a bit about these, so I don't really have to say very much. But if you model by using the configuration model, you come down to this expression for R0, and it's fairly easy to see that if the variance is infinite, then the R0 is also going to be infinite, even if the expectation of a degree distribution is finite. But what does that really mean for a finite population? I mean, you can see it comes out as a limiting result, but in practice, having an infinite variance, well, it doesn't really make sense. And a consequence of this is that the critical vaccination coverage is 1, but what about for finite populations? And similar questions happen in even in homogeneously mixing models. And Joshua Ross, he defined R0 rather than considering in terms of the expected number of infectious contacts made by an individual, now within a framework of a homogeneously mixing model, but the expected number of infections. So if the same person is contacted twice, you only count 1 infection. If you make that assumption, you get an R0 which is dependent on n, and so that gives you a sharper upper bounding branching process. But the interpretation of minor and major epidemics still essentially requires a population size n to go to infinity. I mean, often in control, the aim is to get R0 down to 1. But again, how appropriate is that for finite populations? Because if R0 is 1, the mean size of an epidemic is still infinite in the limit as n goes to infinity. And if R0 is just slightly greater than 1, the mean fraction infected by a major epidemic, what's given by that expression there, which is small. And so, I mean, one approach going back to 20 years, to Ingemar 20 years ago, he defined the threshold value of R0 to be when the final size distribution changes from being unimodal to bimodal. The conjecture that occurred sort of threshold looked like this. As far as I know, that conjecture is still awaiting a formal proof. I think Anders Martin Löf has got a result relating to that, but his limit theorem requires the initial number of infectious to grow to infinity as well. But as far as I know, this hasn't really been formally proved. I think Valerie has also seen similar scaling in some work on epidemics on networks, or rumours on networks. So the other thing is there's no real sharp change in the threshold for finite n, so perhaps control should be more like trying to control the probability the size of an epidemic is larger than some specified value, or the number of people infected in some sort of vulnerable groups is controlled. Coming back to network epidemic models, I've listed it down here, a few areas where I think further work is needed, and many of these have been already mentioned in earlier talks. So one is dynamic networks, including the effect of the epidemic on the network. I've already mentioned a bit about clustered networks, that mathematically tractable models have a tree-like local structure. Another point one perhaps can make is that one often looks at degree distribution, clustering coefficient, and degree correlation, but they don't sort of characterize the network. And it's possible to have distinct network models which have the same sort of degree distribution, clustering coefficient, and degree correlation, but have different epidemic properties. So caution is sort of required if you're trying to extrapolate results from these rather sort of perhaps unrealistic models to real life networks. And one perhaps would like to know which of these models are closest to real life. And also sort of non-SIR models, SIS and SIRS, but as I think Peter said, this is a very difficult area. And one final point, this is rather personal, it goes back to work with Peter Neal. I mean, I think in many ways it's pretty unrealistic just to have in these models you can only infect if you've got a static network along the edges of the network. And I think in real life that's pretty unrealistic. You're likely to meet somebody on the train or a supermarket or whatever who you have no connection with whatsoever. So you can superimpose sort of homogeneity mixing on top of this sort of network structure. And that's what I call casual contacts. And so Peter Neal and I did this work a few years ago. And what we've got here is so this is the probability of a major outbreak, but it's also, because the infectious period is constant, it's a fraction infected by a major outbreak. And we've got two choices of degree distributions, both with mean degree 8, a scale 3 distribution, and a constant degree distribution. And also two models, one with no casual contacts, the dotted line, and one with casual contacts, the solid line. And what you have to look at is, I mean, these lines might look close, but it's a vertical distance between these lines which is important. So certainly if you've got a constant degree distribution and then you add in these casual contacts, you get a big difference. I mean, for example, if P is a probability to infect a local neighbour, I mean, if it's in this sort of regime here, then the chance of a large epidemic is 0, but once you put in these casual contacts, it goes up to 0.75. Okay, the last topic I want to talk about briefly is estimation in an emerging epidemic. And so I think the ideas here go back to a paper by, at least as far as the paper by Jacko Wallinger and Mark Lipsitch in 2007. The notation is different to what I presented here, but I think the key idea, or I hope the key ideas are the same. So let's suppose that infectors have IID infectious profiles, what I'll call lambda A. This could be a random. Where A is so lambda A is the rate an with infectious age A creates new infectives. So this is the intensity of could be random, of the point process Xi I described earlier, giving you the births in the general branching process. So the real-time growth rate then satisfies this equation here, and R0 is just given by the integral of this expectation from 0 to infinity. Now you can define what can loosely be called an infectious contact interval. So basically you take this this E of lambda of t, and you scale it by R0, and this gives you a density, and that would be the density of what we call the infectious contact interval. And then mw of theta is just the Laplace transform of that, or moment generating function of that. And so you then get this equation here. So that is just given by the moment generating function given by this expression here. And so R0 times mw of r equals 1. So if you know this infectious contact, where are we? This infectious contact interval, if you know that, and you observe the exponential growth rate, then you get a rather quick estimate of R0 by just this expression here. Okay, and then Christoph Fraser generalized that to the households model. So now the infectious profile, I call it lambda naught of A, and now it integrates up, its expectation integrates up to 1. So now an infective infectious age A makes global contacts at this rate here, mu g times this process value, and it contacts any given susceptible in this household independently at that rate. So global contacts emanate from a typical single household epidemic, T times units after that household was first infected at some rate beta HT, which is, I'll write it in this form here, where this quantity WH of T depends just on the household structure and the within household disease dynamics. So as similar to before, we now let MH of theta be the Laplace transform of this WH of T. Then R star is just given by mu G times MH of 0. The equation you have to give you the growth rate just reduces to that. And so what that means, if you know what this function, what this Laplace transform is, and you observe the growth rate of in a household's model, you can estimate mu G by this expression here, and you get an estimate of R star. Okay, well, there's two difficulties with that, or at least two. One is actually, in his examples in his paper, Christoph used historical data to estimate the within household infection behavior. But in an emerging epidemic, it may not be appropriate to use such data, and instead you're going to have to estimate it from the epidemic which one's observing. And the second problem is actually working out what that growth rate is. I don't think I've got time to go through the details, but if you've got a Markov model, I think Lorenzo said a bit about this, then you can, it's fairly easy to get a matrix method to work it out. But in general, that's not possible. And Christoph used some sort of approximation which works well if the household sizes are small, or the infection is not strong within the household, or if this infectious sort of contact interval has a small variance. Well, before Dennis throws me off, I just want to say something about estimation in an emerging epidemic in a household setting. So this is 3 minutes, okay? This is work currently doing with a research student, Lawrence Shaw. So this is just an example of what might happen. So you've got an SIR epidemic, and it's a very large population. That's just to make sure the branching process approximation worked well. Amongst households with sizes uniformly distributed on 1 up to 5, where typically infective makes global contacts at overall rate lambda G, and contacts any given susceptible in its own household at rate lambda L, and the infectious period has an exponential distribution with mean 1. And what I'm going to concentrate on here is just how do we estimate lambda L. So we just want to estimate lambda L from observing, after 1,000 individuals have become infected, I want to estimate, or we can estimate the growth rate, etc. I'm going to just concentrate on estimating this local infection rate, lambda L. Okay, well, one thing you might do is, well, look, I'm going to use the usual final size distribution for an epidemic within a single household. I've observed a whole number of single household epidemics. So I look at all the epidemics that are finished in the households. I mean, I might not know in practice, but from the simulations I do. And I use that to estimate lambda L. Well, if I do that, I get this histogram here, which is clearly hopeless, because the true value is 1, and this gives you something centered about 0.3. Well, if you think about it, well, actually the epidemic is sort of emerging, and you're underrepresenting the epidemics you've seen that are finished in households are more likely to be small epidemics and large ones. So let us instead use some censoring, and if the epidemic is still going in a household, of course in practice you may not be able to observe that, let us just say, well, we know its size is at least what its current size is. And then you can estimate lambda L doing that, and you get this histogram over here. And this is now a slight overestimate. And what you can do instead is you can use sort of multi-type branching process theory to give you the correct answer, because in a multi-type branching process, that's going to grow exponentially at rate R. But also, the theory tells you the number of individuals of the different types stabilizes. And you can use that stable distribution, and you can also work out the households which the epidemics have finished. It tells you how many roughly of different of those you're going to get. So you can use that information to feed into your to estimate lambda L. And if you do that, you get this green histogram there, which works. Okay, so this is just what I've just said, but I think similar issues are likely to arise. This is quite a toy example, but if you're estimating when you've got an emerging outbreak, then you've got to be very careful, I think, how you actually model the data you're using, because the emergent nature of the epidemic can actually affect the distribution of things like within household size, the single household epidemics. Okay, so just a closing remark before I hand over to Tom. Branching processes have a very rich and very well developed theory, I think mainly perhaps to their linear nature, and I think they provide a very fertile ground for investigating the early stages of epidemics in large populations. Okay, thank you.
I don't know how you and Tom want to play this, but maybe if we just have questions that are very specific. If they're more general questions, we might finish with some more general questions after both talks. So any immediate questions? Peter?
Yeah, why was there a slight overestimate in the...
It's because...
when you censor the data?
Well, yeah, but you have to censor it properly, because you need to take account, you need to know exactly what you're actually... what determines the distribution is... it comes out of the asymptotic theory of branching processes and how the population stabilizes. And it doesn't correspond to just the usual household size, single household size distribution.
Wrong center, kind of wrong centering.
Yes, okay, that's one way of the model. That it's not just straight right censoring. There's more to it than that.
Just how quickly does it look like asymptotic results in the branching process? How many generations does it take before it is asymptotic but still not influenced by the epidemic?
Well, that's something. I perhaps should say we did this. Lawrence gave me these figures on Friday, sort of thing. So I haven't really had time to sort of. I suggested things he looks at, like reducing the size of the population, and I don't know the answer to your question, but it's obviously important.
Okay, shall we move on to Tom, and then we'll ask Frank to come back on the stage for questions at the end.